Thank you for joining us today's webinar. My name is Chin Nguyen. I'm Technical Application Specialist at Dolomite. So this webinar today is one of the webinars series. We call it Microfluidic 101 with Dolomite. So this will be delivered every last Thursday of each month along 2021. So today our topic is guided to droplet and particle generation. So the agenda today will be including a presentation and Q&A section. So during my presentation, if you have any question, feel free to write down the question in question box, and we will try to directly deliver to you, all of you, in Q&A section. So the content of presentation today will be including introduction about the droplet and particle type, and after that we move to the droplet and particle generation. So as we already learned about the microfluidic technology in the first section, first webinars of this webinar series. So the microfluidic technologies enables formation of the high molar dispersed droplet in the range of the micrometer to hundreds of micrometer with complex structure like emulsions, double and multiple emulsion, encapsulated gas bubbles, generous particles, and hybrid materials. So droplets also can be used at microreactor to make a complex formation as sample can be confined, dilute, mixed, split, or analyzed. So today the microfluidic key applications in wide range of application area, including the molecular biology, particle and nanoparticles generation and manufacture, simulation of porous media, and continuous flow chemistry. So in all of this, the driver is high value cost and time save new capabilities and processes development rather than a low cost is the system and experiment. So let's talk about the droplets. What droplets? For this section, general term droplet and particles are used as follows. Like a droplet is a liquid and gel suspended in immiscible fluid, and a particle is a gel or solid which may be in a continuous fluid, but may also exist on its own, for example, like the powders. So why is the droplet are droplet important? Because the droplets are everywhere. So for example, like droplet form and emulsion are key constituent many household and laboratory product manufactured at own scale. And nanoparticles also very important for enormous array of applications, and droplets are also rapidly becoming the biology and chemistry reaction vector of the future, and the nanoparticles and the particles are become increasing the common drug delivery method. Okay, so there's 9 generic way to make a simple droplet from 2 components. So we have dispersed phase, gas, liquids, and solids. We have dispersions, medium, gas, liquid, and solid. So we can make the gas. We can make the gas in liquids and gas in solids, like form and solid form. We can make a liquids in gas, liquids in liquids, liquids in solids, like liquids aerosols, emulsions, or zero. Or we can make the solids in gas, like solids aerosols, or solids in liquids, like straw, or solids in solids, like solid straw. So today, the discussion is about the system with the liquids continuous phase. So we use the dispersion medium as a liquid. So it's many variants are possible in this. So most Dolomite use work with the droplet and particle in liquid continuous phase. We have 3 different types of droplet. Type 1 is emulsion, which both the dispersed and continuous phase jointly form the product of interest. flexible like foam or creams. Or type 2 is the droplet. So the only droplet of interest and the continuous phase, the fluid is the secondary interest carried for the droplet. So we including the simple droplet where droplet is composed of single fluid such as alginate gels or polymer particles. Or it could be the complex droplet where the droplet is formed from 2 or more fluids such as the core shell particle or xenos particles. With type 3 is the encapsulation. So the content of the droplet are the key factor. So we have homogeneous payload droplets where each droplet carries the same payload in the same quantity. Or we have heterogeneous payload droplets. So where the droplets contain units payloads. So for example, like shell suspension for analysis. So for segment, we have many types of droplet and many ways to make a droplet. So we can make the droplet by segmented flow to with the T-junction. So we're using the droplet phase and dripping to the T-junction in continuous phase to make up the larger side of droplet than the junction side. Or we can make a single emulsion or double emulsion. Or we can make a cell encapsulation by placing one of number of cell particles inside the droplets. Or we can make the nanocrystallization process or xenos particle by mixing two streams to forming the particles with the heterogeneous surface properties or with the subsequent isolation of the reagent into the droplets. So in this case, the droplet have role as a microreactor to make up the nanocrystallization inside. So the microfluidic droplet forming technologies. So today there are 3 main methods used for forming droplet and particle using the microfluidic. So this, in order to the important like the paper or number of users, we classify it as orders as following. So we have a core flow stream or T-junction stream and flow focusing stream. So with different the type the microfluidic method, so we have different droplet particle ring. So with the core flowing stream, we can make it from nanoparticle size to the microparticle size. So from microparticle size to millimeters the particle size or droplet size, we use a flow focusing stream. And with the from micro larger than the millimeters of the particle or droplet size, we have T-junction stream. So the microfluidic have showing the very good molar dispersion from 1 to 5% with diameter wiring from the nanometer up to the 200 more than the 250 micrometer, and with a very high output per channel from 1 Hz to 1 megahertz, depending on the technology. So with the microfluidic particle generation is now a major application area for Dolomite. So we have established the particle engineering group to work on applications, and we make a major particle type, including the API encapsulation in PLGA. We include the encapsulation of the aqueous API using the multiple emulsion with the particle size ranging from 50 nanometer to 50 micrometer. We also make work on the liposome generation to make the nano liposome to Zen liposome with the microparticle size, microsite. And we work on the hydrogels, for example, like agarose, alginate, polyacrylamide, gelatin, or PEGs. And we also work with the polymers with beads like polystyrene or PVD-PB. So here is our single channel system, which the commonly used in R&D scale, in lab scale. So in this system, we have 3 pressure pump, basic pressure pump, with 1 pressure pump for the inner phase or droplet phase delivery. And the second pressure pump we're using for continuous phase, and the third one can be used for many purposes, like we can introduce the third component or reagent into the microfluidic, or we can use for priming or the flushing the purpose before and after the experiment. So the pressure pump will connect to the microfluidic chip by using the tubing and the valves and the connector. So the microfluidic chip is located under the microscope to visualize all the process which occurs inside the microfluidic chip. So depending on different applications, so different configuration of the system can be obtained. So we generate the very complex or very flexible the system. We can adapt with the different the application. So with different application, we also using with the different microfluidic chip. For example, like with the 3 flow focusing microfluidic chip or the droplet junction chip, we can make a droplet and microparticles. Or with the 5 input chip or micrometer chip, we can generate a nanoparticle with flow focusing method. So for scale-up system, so we have a Taylor scale-up system. So the Taylor system will increase the output by 3 distinct ways. So first, it could be increase the flow rate through the individual junctions. It can increase the number of junctions working in parallel. And here you can see it's 1 Taylor microfluidic chip. We have 7 parallel channels we can integrate in 1 chip and working together. So it can increase the production rate up to 7 times compared to a single chip. Or otherwise, we can also increase the product by the increase number of chips working in parallel. So with the Taylor chip, we can we have up to 10 Taylor clamp we can use for running microfluidic with 10 microfluidic chips working together. So it means with 1 Taylor clamp modules, we can allow the typical flow output of 3 ml per minute of droplets from 1 microfluidic chip with 7 chip junctions. So for scale up to 10 clamp modules, which would be increase the flows of output up to 30 ml per minute, which means it can allow the system can have a production rate up to a ton per month of the production rate. So let's move to the droplet generation method. Traditionally, so the emulsions formed by the best method with, for example, like the using high shear methods such as the sonication or homogenizers. And these methods can produce a very large or huge amount of materials, and it can be quite simple to use. However, with these methods, the particle size polydisperse, so we need to filtering of the product after the formation. And the high shear stress or high input energy can also cause problem with the encapsulated payload, so it can be destroyed the encapsulant during the encapsulation process. With the microfluidic methods, it offers a number of the significant advantages, like it could have production rate up to 25 kilograms per day, the droplets, and it can generate a very highly monodispersed particle and droplets, which typically is from 1 to 5%. and it turn over to any particle size, and it also complex particle can be also produced, like multiple emulsion or zealous particles. The mandibles of the real-time QC and wiring formation methods, we can allow we have GMPs compatible and consistent and reproducible. So this graph showing what difference of the advantage of the microfluidic method with compared to batch methods. So with the microfluidic method, it shows when monodispersed and better monodispersed, and compared to batch methods, we allow to generate the polydispersed of droplet and particle. So this one showing the production rate of product capabilities of the microfluidic method compared to the best method. So with the microfluidic method, we can do the scale up to the 10 kilograms per day. However, with the batch mixer or sonication with the batch method, we can do is up to 10,000 kilograms per day. So for droplet controlling droplet size, so we have two ways to control the droplet size. The first way is that using different chip junction size. So with larger junction size, we can form the larger droplet, and smaller chip junction size, we can form smaller droplet. The droplet also can control the size within the same chip by adjusting relative flow rate of the continuous phase and droplet phase. For example, increasing the flow rate of the continuous phase in here, so you can decrease the droplet size, or when you increase the droplet phase flow rate, you can increase the droplet size. And if you increase both of the continuous phase and droplet phase flow rates, you can increase the production rate. And in this case, the setting limit will occur as the maximum flow rate that can be achieved. So based on different the flow rate ratio condition, we have different droplet generation modes. Like we have dripping region, which we can form the very stable droplets. Or we can make a jetting region when we're flowing too fast in the both continuous phase and droplet phase. Or we can make a chaotic by the adjust ratio of the flow rate ratio. And we also have a backflow is unwanted the region mode in microfluidic when we achieve the pressure we have pressure imbalance to continuous phase and droplet phase. So this graph showing the variation of the droplet size and frequency by the changing droplet and carrier pressure. So we will have a stable dripping region in here with different particles droplet size, and we will have the carrier backflow limit, droplet backflow limit, and jetting limit by just changing the pressure relative pressure ratio, flow rate ratio. So here showing one example to see the typical droplet size range possible from a single channel. So in this, we pumping the droplet phase into continuous phase in single channel chip, and we keep the constant of the pressure of continuous phase and just increasing of the droplet phase pressure. So it means we can increase the flow rate ratio between the droplet phase and the continuous phase. So the pressures of the droplet phase will be increased from 50 until to 3,000 millibars when we keep the 1,000 millibar the continuous phase. So we can see the drop when we increase the continuous droplet pressures, droplet phase drop pressure. So we can achieve the bigger droplet We can achieve up to the target mode occurs when we have larger ratio between the droplet flow rate with continuous flow rate ratio. We can create more complex droplet types if required. For example, like double emulsion in here or multiple emulsion in here for advanced application. Or we can make genus particles by just introducing the different reagent into the chip to generate the different heterogeneous surface properties of particles. For particle generation, so we will learn how do we use the microfluidics to generate particles, and to better understand about how we do with microfluidics, we will give some example for this section. Is for example like hydrogel with polymer with microscale PLGA particles or PLGA nanoparticle and liposomes. With the hydrogel with, actually the hydrogels produced by both methods, chemical dilation or thermosetting. So with chemical dilation, we have two reagents combined, and they are pinned out at the tip junction, and dilation will occur in flow or in collection vector by means of introduction of the third component. And the payload of encapsulant is typically the brown in one or in both of the equal slide. For thermosetting, the material we have will be taken above its gelling point to melting or degree viscosity of the material, and after that it's pinched up at the temperature controlled junction, and it will collect and thread through the cooling process. And in this case, the payloads can be brought in on a hot or cold upper slide. So the typical issue can be achieved in this process from working with the viscous material. So usually with hydrogels, with production, the material also viscosity very high, so it can cause the product. We can cause the high back pressure and high flow resistance. And also because we work with the viscous material, so it can have challenges in output product. So it's not easy to increase the output of product when we use high viscosity material. And dilation process also it can be wiring occurs in the wiring time, like to be quickly to happen, or it can take a long time, like a day or several days. And also the matching of reagents, one of the issue, for example, like emulsion stabilizing oil with aqueous component and custom design chip. So here some example for hydrogel the production, like we make a alginate bead to do the cell encapsulation or micro encapsulation or protein encapsulation or API encapsulation. We can make the agar or and gelatin beads to study about the cell and bacterial encapsulation or protein and API encapsulation. Or we can make a polyacrylamide bead to with measurable and non-porous form with oligonucleotide functionalization beads for enhanced ionization capture and to enable the passage through the microfluidic channels, and the heavy cross-links form to it will be applied for therapeutic material, for example, like radioactive isotope. So what problem the microfluidics solve for this hydrogel application? The first is the monodisperse of the sample. So with the microfluidic technology, the size often important as the bits have to pass through the restriction. And the second is the consistency of the loading. So for example, like average of 150 or 100 cells per bit can be encapsulated. And the third one is low energy input. So with low energy input, it can make sure that the microvolt or encapsulation of drug can remain, or bacteria can remain undisturbed. And the fourth is the ability to control to the environment of the payload. So for example, like during encapsulation, agarose cells never experience temperature above the 36 degrees C. So with a microfluidic, we can control the environmental payloads very easily. And finally, to avoid the need for non-trivial size selection by manufacturing as target size. So next example of the microbit for using the microfluidic technology is the polymer bit. So in this case, bits are manufactured by undertaking cross-linking reaction on performance droplet. So in this case, the polymerization of cross-linking process can be initiated by UV initiator or thermal initiator of chemical agent. For example, the ammonium sulfate persulfate can be used as a chemical agent for this application. So in this case, the polymerization can be undertaken in continuous phase flow, or it also can be undertaken after the collection in the vessel. So the typical issue may come from the working with the viscous materials. We can enhance, increase the back pressure and flow resistance, and it also the issue can be because working with viscosity material. So yeah, the enhancement of the output is one challenge, and it could also the prevention of the polymerization in reservoirs also important the challenges because if the polymerization in reservoirs occurs, so it can destroy the microfluidic system. And the matching of the reagent, like for example, like emulsion stabilizing oil with the aqueous component and custom design chip. So here, so is some example for polymers beads production by microfluidic methods. So we have a cross-link PVA bead, which generation of the PVA beads with the precisely control side for implantation into a thermosite. So the packing of such bead restricts fluid flow and consequently access nutrients to the site. We can make the polystyrene, divinine, benzene beads with creation of the distributed multiple layer array for medical device and functionalization of the multiple bead to create a separation column with enhanced resolution and prevent occurrence of preferential part. And we can make up the PMMA beads from the microfluidics. So we create the creation of the medical device that encapsulates radioactive isotope for implantation into thermosite. So what problem the micro solve for polymers beads production by microfluidic method? First, with the microfluidic we can make a monodispersed sample lines. For example, like this, in this case, the size is very important as the beads have to pass through restriction. And in column packing, correction monodispersed to prevent. And in column packing, it's important to create a bimodal or trimodal distribution to minimize porosity. And the second is the ability to expand beside the volume. So the particularly important in encapsulation of the radioactive isotope. And it's also ability to adjust the product on the fly, for example, like changing loading particle size without any retooling. And the final is the ability to generate multiple value run in a day with the Microfluidic technology. So next example, we will learn about the Microscale PLGA particle production using the Microfluidic technology. So in this one, so in the graph showing the system setup for microparticle PLGA particles production. So we have 3 pumps, with 1 pump for continuous phase, which contain the carrier fluids like water or PBS solution with the surfactant, and the other pump with pumping with the polymers mixing or PLGA that is dissolved in the solvent and used as the droplet phase in here. And finally, the final pump, it could be used for priming the fluid, for flushing or priming before running experiment and after experiment to cleaning the system. So the droplet tip with 3 flow focusing droplet tip will be used in for this application. We can allow to generate up to from 60 to 100 micrometers of the droplet. So in for this application, the inner phase, the droplet phase, we use the PLGA dispersed in the lithium as a solvent and pumping to microfluidic chip with flow rate of the 20 microliters per minute, and the continuous phase is the water or PBS solution with using the PBA as a polyvinyl alcohol as a surfactant with 1%, and it's flowed to the microfluidic chip with 50 microliter per minute. So we can make around 100 micrometer of the droplets which contain the PLGA DCM inside and dispersed in the water and PBA solution. So after formation of the droplet, so the solvent extraction will occur. So it means the lithium will be diffused from the droplet side into the water phase, and it will leave the PLGA microparticles, and it can decrease. It also decrease the droplet of particle size. So here showing the process under the 5 minutes of the solvent extraction. So the droplets phase after passing through the microfluidic chip have a size around 100 micrometer, and after 5 minutes, so it can generate 23 micrometer of the PLGA bead. So we use 3D pores microfluidic chip with a new 3D pore technology of Dolomite. So it can prevent the polymer deposition contact with the channels, and it can have the long runtime without blocking with working with the polymers. The next example for particle generation is nanoparticles, liposome and PLGA nanoparticles. So in this case, we will use the flow focusing method. It's for making a nanoparticle. So the liposome or PLGA nanoparticles are formed using a process of nucleation and growth. So in here, so we making a stream between the polymer dispersed in solvent and continuous phase like the water, and make a laminar flow. So with the we have the mixing step. We have in mixing step we have the different steps for nucleation or grow and also shipping to making of the nanoparticles. So the particle size in this case controls by just adjusting relative the flow rates of polymers and aqueous solution. So for encapsulation process, the API of drug can be brought in on the droplet phase light. In here, for liposome, we use the hydrophilic API because the liposome is the dispersed in the ethanol and alcohol, and with the PLGA we use the hydrophobic API we dispersed in organic solvent like DCM. So in this case, we can make up the encapsulation of the drug or API inside the nanoparticles. Here, showing the system setup for PLJ nanoparticles. We have similar with the microparticles PLJ. We have using two pressure pump for pumping of the interface and continuous phase into the microfluidic chip. So in this case, we use a 5-input microfluidic chip to make a flow focusing the stream inside the chip junction in here. So we introduce the afterphase, the water by pumping in this way, and the interface including PLGA dissolved in acetone at solvent and pumping past to make up the laminar stream after the channel junction in here, and the sample will be collect after going out the microfluidic chip. So here showing some the results in the PLG nanoparticles. So we can make a few milligram per hour from with the size ranging from 10 to 500 nanometer by the changing flow rate ratio. So in this graph you can see when we decrease the flow rate ratio, so we can increase the the particle size. So for liposome production, it's similar to PLGA nanoparticles production. So we also using the flow focusing methods to make a focus stream between the lipids in ethanol and water phase. So the lipid cell assembly will occur in the mixing state of the microfluidic chip, and it can generate a small laminar liposome. So for liposome particle size controls, we also controls by changing the flow rate ratio between the water phase flow rate in divided to the ethanol flow rate. So here showing microfluidic setup system setup for liposome nanoparticles. So we also very similar to with the PLGA nanoparticles. So we have one pump to pump in the continuous phase with the water or PBS solution, and another pump will pump the lipid and ethanol in as the interface to make a focus stream using the 5-input chip or micro mixer chip to achieve the different particle size range and different production rate. So by just changing flow rate ratio in here, you can see we can achieve the different flow rate, different particle size, and also using the different chip geometry, we can also achieve the different flow production rate and different particle size. So in this case, particle size were controlled in the region of the 60 to 250 nanometer by the changing the relative flow rate ratio and changing the chip geometry. And for this one, we will learn about the Zen liposome. The microparticles of liposome can be generated using the microfluidic methods. So in this case, the Zen liposome can be produced with diameter range from 20 to 200 micrometer. And in this case, two-step method developed by Portet et al. So step 1, we will make a form of the water in oil droplet using the Dolomite system, making a droplet water in oil. And step 2, to form the liposome by just passing the droplet through the lipid monolayer. So here showing some graph showing scheme showing for step by step making of the Zen liposome. So the first step is the making of droplet which contain the layer, the lipid membrane, one layer, and after that is a pass through the one wire which contains the one oil and the lipid membrane, and it can make a bi-lipid membrane with a microparticle droplet in here. So for the step 1 setup, it's very similar to droplet system, generation system. So we have two pumps, with one pump for continuous phase and the other pump for droplet phase, pumping to the droplet junction chip to generate the droplet particle. So a range of droplet channels available for this application with the different droplet size. And for flow focusing chip, we can make up to 50 micrometer to 190 micrometer chip junction, and it can generate the 20 micrometer to 200 micrometer. We have the T junction chip with size of the 100 micrometer, so we can make a droplet from 100 micrometer to more than 400 micrometer. So for scale from the lab to production, with the scaling up process, Dolomite recommend a stepwise approaches. So the first is initial steps using a single channel chip to characterize the process, like with testing and analysis at the Dolomite site. And the second is the validate process at the user site using the Dolomite single channel system. So we use a single channel system for validate process. And the first one is the validate process scaling up using the multiple chip channels. So we can increase the production rate by increase the chip channels. And finally, the scale up to production level using the Taylor system, as we can integrate the up to 10 modules of the Taylor chip working together. So here showing some scale example. So let's say if we have we need to do production rate 1 ton per month, it means we have to make up the 100 mil per minute production rate at the working day, like 5 days per week and 8 hours per day. Or we can make it with 25 mil per minute if we run the system over all the time. So here showing the one example for making a PLGA microparticle using Taylor system with the 5 chips working together. So for this system, you can see in here this video from our customer side. They are making a microparticle PLGA using the Taylor system with including the 3 working with the 5 microfluidic chip working together in here, and you can see the product can be collected in here. So the system will be have a custom the chambers, the press chamber, and the reagent chamber to adapt using with larger amount of reagent. And from here you can see more clearly how the fast of the production rate can be achieved using just 5 microfluidic chip working together in one system. So in here, with the 5 microfluidic chip working together, it can be running at 12.5 mil per minute. It means if it's working all the day, all the time, per week or per month, so it can generate around 500 kilogram per month, or half ton per month production rate. So summary, the microfluidics is no longer just an academic pursuit, and many of key applications are now in particle engineering. So with the polymeric microparticle synthesis for API encapsulation, for food, for cosmetic liposome or separation particle size, or we can make up the nanoparticle synthesis for API encapsulation, for food and cosmetic, for liposome, for catalyst, or for quantum dot application. And Dolomite products are particle engineering team which enable an user to achieve the high performance of experiment reproducibility both in both chemistry and engineering. And we have a specific system with very flexible to target specific application, for example, like nanoparticle system, microparticle system, emulsion system, double emulsion system, and many systems. So we also are always interested to work in collaboration to develop a new application with the customers. So Dolomite process also can be scaled to pilot plant production level using a multiple module tailor system. Okay, so I finished the presentation today. So now we will move to Q&A section. So if you have any question, please feel free to write down the question in the question box, so we can have discuss right now. Okay, so yeah, please write down your question in the question box. So I will try to let you all of you know all of the question. Try to answer all of the question in this Q&A section. Yeah. So, do you have any question? And also, just remind you for the next section for our webinar series for next last Thursday of last Thursday of the next month. So the topic will be focused on PLGA microparticle production. So if you have interested on this topic, please visit to our website and have registration for next webinars topic. I don't see any question. Please I hope I can, for this webinar, I can share with you about the information, all of the application related to droplet and particle generation using Microfluidics. And even though if you are doing the particle and droplet application, if you got any issue or any question on your specific application, just feel free to ask. Any question? Okay, if you don't have any question, yes, that's okay. So if you have questions later, just feel free to email us. So we will email us to Hanoi office at Hanoi office at brightshade.com. So I will try to deliver your question later through the email. So and okay. 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 So I got one question in here. So I will let you know about the question through the email. Thank you very much, everyone.